I did want to point out one more thing, and this goes back to question 9 from the last video, but instead of using the calculator to find the 90%, you could have also used your table of values. If you go to your t-distribution table of values, okay, we had 1.65 as our critical value. So if you come down here where it's infinity, okay, that's going to give you infinity. You got to remember that as the degree of freedom gets larger in your t-distribution, so as this number right here, your degree of freedom gets larger, the distribution gets closer and closer to a normal model. So if we come over here to infinity and we look at the critical number of 1.645, right underneath it, it tells you the corresponding confidence level, which is 90%. All right, so just one other way besides the calculator on how to see how to find that 90% confidence. Okay, next question. So a compact disc manufacturer wanted to determine which of the two different cover designs for a newly released CD will generate more sales. The manufacturer chose 70 stores to sell the CDs. 35 of these stores were randomly assigned to sell CDs with one of the cover designs, and the other 35 were assigned to sell the CD with the other cover design. The manufacturer recorded the number of CDs sold at each of the stores and found a significant difference between the mean number of CDs sold for the two cover designs. Which of the following gives the conclusion that should be made based on the results and provides the best explanation for the conclusion? So this one, our answer actually is D. We're going to say that it is reasonable to conclude the difference in sales was caused by the different cover designs because the cover designs were randomly assigned to stores. So remember, the random assignment is what allows us to say cause and effect. Without random assignment, we do not have cause and effect. Right? If we look at these other options, it says it's not reasonable to conclude that the difference in sales was caused by the different cover designs because this was not an experiment. It was an experiment. They did implement a treatment. Okay, they randomly selected stores, and the treatment was the different covers on the CD. Okay, so this was an experiment. For B, it says it's not reasonable to conclude that the difference in sales was caused by the different cover designs because there was no control group for comparison. So we did have two different groups that we could still compare, right? We had two different designs that were randomly assigned to stores. So we were still able to compare. Okay, it's not reasonable to conclude that the difference in sales was caused by the different cover designs because the 70 stores were not randomly chosen. So once again, the random assignment of the treatment is what allows us to infer cause and effect. So just because these stores were not randomly selected, the treatment was randomly assigned to each of these 70 stores. All right, we already said D was the correct answer. E said it is reasonable to conclude that the difference in sales was caused by the different cover designs because the sample size was large. And that's not going to be correct. Remember, large sample size, that's what we use to check for normality. Large sample size isn't what we use to determine cause and effect. If we look at 11, the manager of a public swimming pool wants to compare the effectiveness of two laundry detergents, detergent A and detergent B, in cleaning the towels that are used daily. As each dirty towel is turned in, it is placed into the only washing machine on the premise. When the washing machine contains 20 towels, the manager flips a coin to determine whether detergent A or detergent B will be used for that load. The cleanliness of the load of towels is rated on a scale from 1 to 10 by a person who does not know which detergent was used. The manager continues this experiment for many days. Which of the following best describes the manager's study? So if we look at our options, we have a completely randomized design, right? A randomized block design with detergent A and detergent B as blocks. A randomized block design with washing machine as the block. A matched pair design with detergent A and detergent B as the pair. And an observational study. So it's not an observational study because a treatment was implemented. We had two different types of detergents and different loads of laundry got one or the other type of detergent. So we know it's not an observational study. All right, in this case, for it to be a block design, then what would happen is we would have to be breaking up the loads of laundry by some sort of characteristic. Okay, if we had different colored towels, if we had colored and white towels, right? And then we flipped a coin to see which detergent, we would use for the colored towels the first time, right? And then every time we got a batch of colorful towels, we flipped the coin to see what detergent it got, and then every time we got a batch of white towels, we flipped a coin to see what detergent we got. That would be an example of blocked. You're breaking it up into two subgroups, and both of those subgroups will be given both treatments. All right, and in this case, we didn't do that. We just had one washing machine. All right, it got filled up randomly, and then we flipped a coin to decide which detergent we were going to use for that specific load. So block design is not the case for this one. It's not going to be B or C. Matched pairs design is when you have two individuals that you're grouping together and comparing, right? Or you have one individual and you're implementing the same treatment to it. This is not a matched pairs design, right? This is going to be a completely randomized design. Okay, the towels are put into the washing machine randomly. They don't tell us anything about how dirty. They don't give us any information like that. They're put into the washing machine, and then each time we get a specific amount of towels, specifically 20 towels, they flip a coin, and that tells us what detergent we're going to use. So this is a completely randomized design. In the design of a survey, which of the following best explains how to minimize response bias? And so for this one, if we want to minimize response bias, right, what we're going to do is carefully word and field test survey questions. All right, increase sample size. That's good if we want to reduce the standard deviation, right? A larger sample size is always good. All right, decrease sample size is not usually the way we want to go. Okay, randomly select the sample. That is a good technique that we want to use, but that's not necessarily going to minimize response bias. All right, response bias is when something in the survey design influences the response. So the best way to minimize it is carefully design your survey. All right, and so if we look, increase the number of questions in the survey, that's not going to do it either. What we want to do is we want to make sure that we carefully word and field test survey questions. All right, we're looking at the design of our survey in this one. For question 13, for a sample of 42 rabbits, the mean weight is 5 pounds and the standard deviation of weights is 3 pounds. Which of the following is most likely true about the weight for rabbits in this sample? Our answer is going to be C. The distribution of weight is going to be skewed to the right because the least possible weight is within 2 standard deviations of the mean. So if we know that the mean is 5 pounds, all right, then 1 standard deviation below the mean is going to be 2 pounds. All right, and that's going to be 1 standard deviation below. And so for us to go 2 standard deviations below, all right, then that actually gets us at -1, and we can't have a negative weight. All right, so we know that the smallest weight the rabbit can be is within 2 standard deviations from the mean. Right? But we could get larger, right? We could have 1 standard deviation above the mean, right? That could be an 8-pound rabbit, right? Or we could have an 11-pound rabbit, which is going to be 2 standard deviations above the mean, right? Or we could have 3 standard deviations, right? We could have a 14-pound rabbit, okay? We could have some really large rabbits, right, which is going to give this a skew to the right, whereas we have to stop right at the smallest rabbit. We can't have a rabbit that has a negative weight. That wouldn't make sense. Okay, one thing I do want to point out is for A, the distribution of weight is approximately normal because the sample size is 42. So remember, that's kind of playing off of our large counts, and they want you to think, oh yeah, it's greater than 30, so it's normal. But remember, we're using that when we're trying to approximate a normal distribution when we're calculating for confidence intervals or for significance tests. But the distribution of weights itself, in this case, is probably going to be skewed to the right. All right, so for question 15, it says a polling firm is interested in surveying a representative sample of registered voters in the United States. The firm has automated its sampling so that random phone numbers within the United States are called. Each time a number is called, the procedure below is followed. If there is no response or if the answering machine is reached, another number is automatically called. If a person answers, a survey worker verifies that the person is at least 18 years of age. If the person is not at least 18 years of age, no response is recorded and another number is called. If the person is at least 18 years of age, that person is surveyed. Some people claim the procedure being used does not permit the results to be extended to all registered voters. Which of the following is not a legitimate concern about the procedure being used? And so if we look at A, it says registered voters with children under the age of 18 years may be underrepresented in this sample. So remember, it's asking which is not a legitimate concern. And in this case, A would be a legitimate concern. Right? Anybody who has kids, if the child picks up the phone first, then they are going to be skipped and therefore underrepresented in this sample. So A is a legitimate concern, so that's not the right answer. For B, registered voters with unlisted telephone numbers may be underrepresented in this sample. Now, normally this would be a concern, but this question specifically said that they're sampling random phone numbers. So they're not saying that they're pulling it out of a listing, or they're not saying that they're pulling it out of a phone book or anything like that. They're just picking random numbers. So in this case, this would not be a concern. And so that's actually going to be our answer. Our answer is going to be B. Right now, once again, if they did say they were pulling it out of the yellow pages, or if they were selecting listed numbers, then that would be a different situation. All right, registered voters who have more than one telephone number may be overrepresented in the sample. That is a legitimate concern. Registered voters who live in a household consisting of more than one voter may be underrepresented. That's a legitimate concern as well. And people who are not registered to vote may bias the sample results. That's a legitimate concern as well, because there was no part of the questioning that asked if they were registered voters. So for number 15, our answer is going to be B. All right, so question 16. A complex electronic device contains three components, A, B, and C. The probabilities of failure for each component in any 1 year are 0.01, 0.03, and 0.04 respectively. If any one component fails, the device will fail. If the components fail independently of one another, what is the probability that the device will not fail in 1 year? So I went ahead and wrote out for components A, B, and C, we have the failure rate of 0.01, 0.03, and 0.04. And so I also went next to that and wrote, if the probability of failure is 1%, then the probability of it not failing is going to be 99%. And I did the same thing. I found the probability the component does not fail for B and C as well, which is 0.97 and 0.96. So if we want to find the probability that the device will not fail in 1 year, then we're going to go ahead and take the probability of success, which is 0.99 for component A. All right, and the probability of no failure for component B is going to be that 0.97. And I'm also going to multiply that by the probability of component C not failing, which is 0.96. And so if I multiply all of those together, I end up with 0.922, and my answer should be D. All right, I'm going to stop there because I'm almost at my time limit, and I will pick up with question 17.